So welcome again to the Picture Language Seminar. We have a set of very interesting talks coming up with Laurent Salaf-Kost, Jinsung Wu, Nilanjala Datta, and Avi Vigdusson. And today we are very pleased to have Marianne Leitner and also to jointly present our seminar with the Dublin Institute for Advanced Study. And I pass it over to Donja O'Connor, who's the director of the School of Theoretical Physics, to introduce Marianne.
Thank you, Arthur. It's a great pleasure to join you once again for this special seminar by Marianne. Marianne Leitner is a Government of Ireland postdoctoral fellow at Trinity College Dublin, Department of Mathematics. She is a former scholar of the Dublin Institute for Advanced Studies, and she's going to tell us today about integrability, rationality, and convolutions. I hand you over to Marianne. Thank you, Marianne.
So thank you very much. So now okay, I can't see I want to share my slide and I can't see it now. So
there should be a green, but it was in my
slide. I know. I tried it out several times. Just a moment, please. Excuse me, please. It's very odd. So now let me try again. So here it is. Okay. And so first of all, thank you very much to the organizers for giving me the opportunity to present my work here. I give you first an overview of my talk today. So I will first make a survey of the different areas where the Eisenstein-Kronecker function plays an important role. So the first one is in the context of vector bundles on an elliptic curve. Could anyone please confirm that you can hear me very well? And
yes, we can hear you quite well.
Yes, we can hear you, Marianne. Thank you.
Okay, thanks.
And we can see your screen.
So very good, thank you. So in decomposable vector bundles over an elliptic curve, which in the following I will denote by X, have been classified by Atiyah in 1957. Their isomorphism classes are classified by the pair of rank and degree and a point on the curve. And in view of what I'm going to talk about later, the latter plays the role of h bar, of the Planck constant, for elliptic R-matrices. Atiyah did not determine, however, the global sections, which have become important in recent years. So as an example, I'm going to consider the following exact sequence. I'm considering a vector bundle V of rank 2, and this exact sequence given here, where E on the left-hand side is the trivial bundle. So this leads then to upper triangular matrices of the form A, B, 0, 1 as transition functions, where A defines the line bundle L. And for shifts by tau, it is of the form A is equal to exponent x to the 2 pi I m z minus c, where m is up to sign the degree of L and c is a number on the curve. For m equal to 1, there's a canonical solution which is given by the Appel-Lerch sum. And of course, if Atiyah had followed up on this case, he would have found the Mock-Jacobi forms which Zwegas discovered in 2002. So explicitly, when, as in the following in my talk, Q denotes the e to the 2 pi I tau, then mu is given by a fixed z naught here. So mu of z and z naught is given by this, this infinite sum here. And when a of z is e to the, or minus e to the 2 pi I z minus z naught, q to the power of a half, then L is defined by the divisor I give here. So this is minus z naught minus tau over 2, a half period. And the pair given by e to the pi I z mu, comma 1 defines a section in the bundle V I mentioned before. So here in the following, the var theta, the theta here, denotes the classical Jacobi theta function, and I won't use any other theta function explicitly. So what I will talk about can now be formulated as iterated extensions of the trivial line bundle by trivial line bundles. And this means that my transition functions will be upper triangular matrices with 1, 1, 1, 1, 1 on the diagonal. And such functions are quasi-elliptic. The second context is, I would like to mention is Feynman graphs on elliptic curves. So the calculation of Feynman graphs, Feynman integrals on CP1, so genus 0 firstly, can be reduced to that of integrals of rational functions along paths on the Riemann sphere. And this is referred to as multiple polylogarithms. There's a generalization to elliptic curves, which has been introduced by Levin and Brown. And this uses a family of functions, which will play a role later on. I denote them as G with an index n here, which is not a derivative, it's the index for the specific function, which depends on x and is defined for n larger or equal to 0. And these are linearly independent functions and have at most simple poles. So I'm referring here to a specific paper by Brödel, Duhr, Dulat, and Tancredi in 2018. So more specifically, fix an elliptic curve and take, say, k points, x1 to xk on x. Then a class of iterated integrals is defined recursively by the following formula, which won't matter much for the talk here, just to give it context. And you see here that the integral kernels here are given by the functions gn I mentioned before. So this is a recursive definition which starts with gamma for no argument. So this is n2 to nk and x2 to xk, where the n's are integers, non-negative integers. So I'm starting recursively. We have nk minus 1 arguments here and k arguments on the left-hand side. So this when k is 0, then I'm just starting with 1. And the integral may not make sense the way it is written down here, but I don't want to address this in this talk. The point is here that these specific functions I introduced here are regular on R for n larger or equal to 2. However, for n equal to 1, the G1 is given by a zeta of x minus E2 of x. So here zeta is the Weierstrass zeta function, so its derivative with respect to position, I'm omitting here the tau dependence, is minus the Weierstrass p function, and E2 is the difference of the shift of zeta by 1. This is a standard notation. It refers to the quasi-modular Eisenstein series of weight 2. The point here is that the integration kernels, these functions Gn, they're generated by the Eisenstein-Kronecker function, which has the following form. So EF, capital F, subindex tau of x and y, so 2 arguments on the curve x, is given by a quotient of twofold products of theta functions. So the first one at 0 is just is the null theta value, it's a constant, and then I have theta x plus 1 divided by theta x times theta y. And this function we are going to consider in more detail later. The third approach is by elliptic integral models. It has been observed by Alexander Samolochikov in 1979 that 2-particle scattering matrices of 2-dimensional integrable models have the same structure as Baxter's R-matrices for the H-vertex model when the rapidity is taken as the spectral parameter. So the H-vertex model is famously solvable, and the fact that it's solvable relies crucially on the fact that the corresponding Boltzmann weights or energies define an elliptic curve. So you have four of them, and their ratio can be written in terms of the elliptic, the Jacobi functions S and U minus W, S and W, and their product essentially, where S and U is given again by a quotient of theta function, is actually a shift of my Konica Eisenstein function f tau of z at the point 0 when you shift this function by half integer periods in the first and second argument. So here the relation between the U I mentioned here and the z is just multiplication by a constant. So a simple equation has been introduced by Polishuk in 2002 for purely mathematical reasons, and it depends on a second parameter, which is later called h bar, which I mentioned before, the Planck constant. And this is referred to the associative Young-Baxter equation, and it takes the following form. So it's easier than the one we had before. So the one we had before was a cubic, it was cubic in R, whereas this one is quadratic in R and has 3 terms. And please note that this formulation uses, of course, the additive structure on the curve, because W and V and U, W, V, and V prime are all elements on the curve. So to be more precise, the notation here with the indices means that I start with a function which is a meromorphic function of two complex variables, U and V, in a neighborhood of the origin, and which takes values in a tensor product of a twofold tensor product of A, where A is an associative algebra with 1. The pair of indices specifies an embedding of this twofold tensor product into a threefold tensor product. So for instance, when A is a matrix algebra, then R13 UV would be a sum over, matrix elements depending on U and V, and you have matrices in the first and the third factor of this tensor product in accordance to the index 1 and 3 here. So a theorem by Polishuk in 2009 says the following: suppose RUV is a solution of the associate Young-Baxter equation and has a Laurent expansion at V equal to 0, which is given by this form here. So there's a simple pole at V equal to 0. Then the following two conditions are equivalent. Firstly, when you fix, so the RUV is a function of two arguments. When you fix one of them, say V, then RUV satisfies with respect to the coordinate U the quantum Young-Baxter equation, which is given by this expression here. You have again a triple product here. The H bar is fixed here, and the arguments run again over the elliptic curve. An equivalent condition is that RUV is unitary, which means that when you take the product of two copies of R and V, RUV, where you change the sign of one of the arguments, then this should be a scalar multiple of the tensor product of the identity. This was a rather abstract discussion using Messier products and so on. And Berban and Kreusler worked out Polishuk's tensor-weighted solutions of the associate Young-Baxter equation explicitly in 2012. So it turns out that for the individual matrix elements, so when you compute them all out, then you find that the solution just reduces to what is called the Phi identity. It's really, in genus 1, it's really a Jacobi theta function identity. The power really of this Phi identity is visible for higher genus later. So the Phi identity is just the associate Young-Baxter identity where you omit all indices. It's exactly the same equation then. And Polishuk found in 2000 that if RUV is a non-zero meromorphic function in the neighborhood of 0, which satisfies this Q-symmetry property I mentioned here, R of minus U minus V is minus R of UV, and in addition phase identity I mentioned above here, then the R, I omitted I should have replaced the A here, RUV is up to trivial transformations just the Eisenstein-Kronecker function, or, so I'm only talking about genus 1 here, more generally it can be a trigonomic or rational degeneration of this function. So solutions with higher order pole have also been obtained from this Eisenstein-Kronecker function FUV and its derivative, and this is work by Berban and Hendrich. They do, however, not satisfy unitarity, so they do not solve the quantum Young-Baxter equation. So then there are also higher genus analogs that I haven't studied in detail. So there's an integrable chiral pots model where the weights are parameterized by higher genus curve and involve higher genus theta functions. Now I would like to switch to number theory. So again, I use the notation that tau is an upper complex half plane, Q is e to the pi I tau, and let f of tau be given by this Fourier expansion or Q expansion, where the point is that you see I'm summing here over L coefficients f depending on f, or for some integer L, and L starts with 1 and goes to infinity then. So this is a cusp form because the zero coefficient is 0 of weight k on PSL to Z. The space of such cusp forms has a basis of Hecke eigenforms. And I would like now to consider the so-called period polynomial. It's constructed as follows. So you take the integral of your cusp form and you multiply with this linear factor here, take it to the power of k minus 2, where k is the weight of the function f, and integrate over the modulus from 0 to I infinity. And just using binomial formula, you can see that this defines a polynomial of degree smaller or equal to 2, where the coefficients are essentially the periods of f. So power n is the nth period of f. So if, there's some technical notation which doesn't really matter, but for my subsequent formula, let me denote, I'm going now to consider a product of such polynomials in x and in y. So consider a twofold product of such polynomials and take the odd part, so which is odd with respect to x, y exchanged by minus x and minus y. And then we normalize the whole thing with a Peterson scalar product defined for cusp forms. Then I define the following. So the small c sub k here for the weight k, function of weight k, of x and y, and tau is given by a sum over, so firstly, this odd part of the product of the period polynomials divided by some normalization factor times my function f of tau. And now I'm summing over, instead of just cusp forms, I'm summing over all modular forms. And this has a vector space basis in terms of Hecker eigenforms. And what I'm really doing now with regard to what I did before is I'm including the Eisenstein series. And then we have to adapt a few definitions of the scalar product, Peterson scalar product, and the polynomial, but I don't want to discuss this here. The point is now that we, in order to understand some specific number theory behavior of this function here, I consider the generating series, and it's given by this expression here. So for k larger or equal to 2, I'm just taking my small ck I introduced before, and then I add by hand a term for k equal to 0. So the weights are always odd. And so I'm summing over k larger or equal to 0. And a theorem by Donzatier from 1991 says that these functions have particular rationality properties. So this is reflected by the Q here in the formula. And important for us is that this function, this generating function, capital C, which generates my small c's here, that this is given by a twofold product of my Weierstrass, of my Eisenstein-Kronecker function. So you see, this function turns up in many contexts, and I just want to make a few remarks here. So the first thing is we saw in the Young-Dexter context that we are adding arguments. Here, actually, the arguments are multiplied. So I'm not quite sure at this stage what the meaning really is. We have an additive structure on the curve, but I'm not sure about the multiplication here. And also an observation is that, you know, every factor of f here, capital F, is a product of two theta functions in the denominator and two theta functions in the nominator. And the arguments are t, xt, yt, and xyt up to sign. And these four arguments, of course, are not free. I mean, they're dependent, and they satisfy an equation which looks like the vanishing of a determinant. Another remark is that when it is stated that the formula for capital C is actually the easiest combination of theta functions, such that the E2, which I mentioned before, which is a quasi-modular form, drops out. And just as a small check, when we take x equal to 1, then we obtain from the degenerate Fay identity that the product of the two f's here, corresponding to the value x equal to 1, is just a difference of two Weierstrass P functions, which is in particular, there's of course no E2. P itself has only modular forms as coefficients, so it's modular. And moreover, when you consider the unitarity condition for R-matrices of Baxter-Belawin type for n times n matrices, then you find that the unitarity is just essentially the same as the previous equation when you take n equal to 1. So eventually I would like to come to my own context. How did I get interested in the Kronecker-Eisenstein function? And this is by the computation of Virasoro endpoint function conformal field theory. So fields can be considered as operators, and endpoint functions of the holomorphic Virasoro field are given by the functional derivative with respect to the metric. So this is written in this formula here, which goes back to at least Weinberg, but maybe as far back as Einstein. And even so in this talk, I'm considering G equal to 1, so genus 1 only. We are really aim for higher genus, and more specifically, I'm considering general hyperelliptic curves of higher genus. So we are here in a mathematical picture language seminar, so I would like to mention a graphical representation, which is closely related to the problem that motivates this talk also. So for G equal to 1, we can write the endpoint function of the holomorphic Virasoro field as a sum of encoded graphs. So here, I will show you a picture in a minute. Here, gamma is an oriented graph. I'm summing over the gammas here. And this is a function of these graphs. So gamma is an oriented graph with vertices, with n vertices, which are just the arguments of my endpoint function here. And for every I, Zi has at most one ingoing and at most one outgoing line, and no tadpole. Then for every n larger or equal to 1, there is a function which I denote by m sub 2n, which is defined on the upper complex half plane and takes values into complex numbers, such that this encoding function for the graphs is given by this expression here. So basically we have a product of Weierstrass P functions where the argument is a difference of points whenever the 2 points define an edge in my graph. And then I have coefficients, which I claim are modular forms of weight 2n. So m2n is a modular form of weight 2n. And as is another decoration, we have a factor in front of this product here, and this is so C is the central charge here, and I take the power, the number of loops in my graph, and the proof is really the clever use of the operator product expansion of the Virasoro field that I mentioned here. So let me show you briefly a picture from my office in Dice at some stage. So for instance, when n is equal to 3, so I have 3 vertices, then I have the following possibilities to make graphs out of them that satisfy my conditions. So I can take 3 isolated points. I can connect any 2 points and give them an orientation. So the orientation is just bookkeeping. It's not crucial. And I can, well, of course, I can change which edge I choose. Then I can have at most 2 edges that emanate and end at one vertex. Then I can have 2 edges, and I can have a loop of 3 edges, which is not a tadpole. So when the whole formula, the whole proof relies on the OPE, and the OPE is a statement about singularities. But of course, when we have no position, then there's no singularity. So the 0-point function, or modularity, the partition function is constant in position, but it's a function of the metric G. And we saw this before because the Virasoro field is defined as functional derivative with respect to the metric. In genus 1, every metric is known to be conformally equivalent to a flat metric, so we are only considering these, which means that G is a function of the Teichmüller parameter tau in the upper complex half plane alone. And then we can find, so T generates changes of the metric. This means that when I take the nth derivative with respect to the modulus of my 0-point function with respect to the flat metric, then this is an n-fold period integral of the endpoint function of T. In fact, it's actually only n-1 fold period integral, because in the first step, when I do this successively, the 1-point function of T is constant in position, but this doesn't really matter here. The point is that when I'm using now my graphical representation theory, which replaces every edge by a Weierstrass factor, then I'm getting products, integrals, or iterated integrals over products of Weierstrass P. So for instance, here I'm always integrating over doubly occurring vertices. So here the 2 is appearing twice. So the whole thing here will be a function of x1 minus x3. Then I integrate again, and I integrate for x over 3. So I end up with something which does not depend, because both arguments appear twice, something which does not depend on position, which means that only loops will contribute. And the problem that motivates the discussion I'm giving here, presenting here today, is that I actually want to compute such iterated integrals of the Weierstrass P function. And okay, naively, you can try integration by parts, and this is possible. So P has weight 2, so 3 factors of P will have weight 6. And fixing the coefficient is not too hard, and they have lower weight terms. And in particular, you have the E2 we saw before. So the E2 can actually be forgotten about at this stage, because it's not modular, and we know that the result should be modular. So if you want to know what the coefficient is, you can easily reconstruct it by modular invariance. So actually, in order to compute such iterated convolutions, it turns out that it's useful to introduce Konica's modified zeta function. We saw this before, so those who are not haven't fallen asleep yet see that this is actually just the G1 I considered in the context of Feynman integrals. I denote this by Z for a zeta function. So that again is, zeta is again my Weierstrass zeta function, E2 is my quasi-modular form. And it's obvious that C is not an elliptic function, so it almost is. So the addition of this E2 term makes that the function is periodic in the real direction, so it's 1 periodic. However, it fails to be periodic in the second direction, which is due to the fact that Z has a simple pole, so it can't be elliptic. And to come back to Attia's language before, so this bundle V would be spanned locally then by 1 and Z, and then the quotient by the trivial bundle, which is isomorphic to the line bundle, is then trivial. So this is a start here of a study of quasi-elliptic functions, and I will switch now to a more mathematical part. So I want to introduce briefly a few simple definitions. So in the following, I will only consider meromorphic functions that have period 1. And I introduce the forward difference operator, which is given by, so applied to f of x plus tau minus f of x for all x in the complex plane. And I denote by delta to the power of k, the k-fold application of delta, so this forward difference operator. When k is 0, then this is just the identity. And I will denote by k sub k the kernel of the k-fold application of k. And we will say that f is quasi-elliptic if f is in this kernel of k-fold application of the difference operator for some k. So the delta defines now a k1, so a linear map. So k1 are the elliptic functions, so a k1 linear map, and k will be denoted as the union of all these spaces sub k. This is a filtered algebra over the k1 with respect to pointwise multiplication. And we will say, moreover, that that f is special, and we write this as sk, so s for special, if all poles of f are located on the points of the lattice. And moreover, I denote by sk sub k the intersection of sk and k. So briefly a few examples. So k naught is of course 0 because it's the kernel of the identity. K1 is the field of elliptic functions. sk1 is the ring of special elliptic functions. K2 it contains the function zeta introduced before, because the delta of z, to remind you, is a complex number. In the following, by the way, I will denote this delta z, which is this complex number, just by 1 for simplicity, to simplify notations. And as a function in x1, the difference of z of x1 plus x2 minus z of x1 defines an elliptic function, but it's not special for generic x2. This can be changed by multiplying this difference of Weierstrass functions, p of x1 minus p of x2. So then this kills my singularity at x1 equal to x2. However, it introduces second order poles here. And I added this term for symmetry reasons, because you're just recovering the well-known addition theorem for the Weierstrass zeta function here. So the maybe most important mathematical result is in this talk is the structure theorem for sk functions. So firstly, the special quasi-elliptic functions sk form a polynomial ring over the special elliptic functions in the coordinate z. And moreover, it's a free module over sk1 with basis powers of z for k larger or equal to 1. For f in sk since I said I am only considering one periodic functions, I will concentrate only on poles that lie along the imaginary axis or the tau axis. So when x is an m tau and m is an integer, I introduce the notation here f sub l, which is a map from the integers to z, such that the Laurent expansion of f at the point x equal to m tau can be written in the following form. So I only wrote out the singular part explicitly, and then there's a regular part. And the first statement is that this fl of m here, so the m is the position of the pole, is a polynomial. So I write this as fl is in p of l, and this is this object here is isomorphic to the polynomial ring with complex coefficients in the coordinate m. Moreover, when you consider the map sigma, which is defined on the quotient of such special quasi-elliptic functions up to addition of a constant, and this goes into the direct sum of these polynomial rings here, and defined by the class of the function f. So f up to addition of a constant is mapped to this array of f1, f2, f3. These are the polynomials of the Laurent expansion. That this is actually an isomorphism. So the statement is really that the space of special quasi-elliptic functions is actually very nice. So for the elliptic functions, we have a quite well-known but still complicated functional equation. However, the special elliptic functions are much nicer. I would like to introduce a new convolution. So for functions that are special quasi-elliptic, so when the argument, the imaginary part of the argument is between 0 and 2 times the imaginary part of tau, then I define the convolution as follows at the point x. So I take the contour integral over a segment, which a period which is parallel to the x-axis, and the imaginary part of the imaginary part of the variable I integrate over should just be half the imaginary part of my argument x, and the integrand is the usual integrand of convolutions. So there are the following statements. This convolution is nice. Firstly, it maps products. It maps pairs of special quasi-elliptic functions into a quasi-elliptic function. And firstly, it's symmetric, and to see this is just a matter of formulation. So instead of writing x minus z and z, I write x1 plus I1 and x2 plus IY2, and then I can write the above integral as a double integral over x1 and x2. I introduce a delta function here to make sure that x1 plus x2 really sum up to my real part of the x I start with, of my argument here. And this thing is symmetric when I require that y1 and y2 are equal, and both equal to imaginary part of x over 2. So this thing is manifestly, just by looking at it, this is symmetric. And please note that when you take x to be real, then this cannot be symmetric, because then the imaginary part y1 must be the negative of y2. So this is never symmetric. This convolution is also associative, and the argument is very similar. You just add another factor, say h, to the f convolution with g. Another nice feature is that when you have two functions, f is regular between 0 and n times imaginary part of tau, and g is regular between 0 and n times imaginary part of tau, so n integer numbers, then the convolution product is regular between 0 and n plus m times imaginary part of tau. So the integral doesn't pick up any residues. So the nice feature of this space of special quasi-elliptic functions is that it becomes a filtered algebra in at least two ways. So the first one is given with respect to pole order. So when you have two special elliptic functions, f and g, with maximal pole order OF, respectively OG, then we have that the pole order of the convolution product is smaller or equal than the respective orders minus 1. Another filtration is given for the space when you consider the functions modulo addition of a constant, as we did before. So firstly, the nice thing is that when you take such classes and multiply them pointwise, then the product of the classes is not the class of the product, but for the convolution, it works out nicely. The convolution product of two classes of functions up to addition of a constant is the class of the convolution up to addition of a constant. And we have the following statements. So when f and g had respectively are classes in SKR, SKS respectively, then the convolution product of the two is an element in SKR plus S modulo constants. So we have that SK mod C is a filtered algebra with respect to this product using the filtration defined by the forward difference, the delta. One theory which will be crucial for the later discussion is, let me introduce the space V, which is the space of all special quasi-elliptic functions f, which have pole order at most 1. Then up to addition of a constant, the space is spanned by powers of convolution, classes of convolution powers of the the modified zeta function. And moreover, we said that, so since the convolutions define elements in the quasi-elliptic functions, the residue will be a polynomial, and for the specific function, polynomial is given by a binomial coefficient, m-1 over n-1 at the position x is equal to m tau. So let me now switch to the applications. So I come back to my functions g and I introduced in the context of Feynman integrals, and I'm going to consider the generating sequence, which is actually my Konica Eisenstein function I mentioned before, depending on tau, which I omitted here. So f of xy, we write this as 1 over y times the sum n larger or equal to 0, g to the with index n of x times y to the power of n. So then the specific, this can be computed, the specific gn. So the first one is the identity, g1 is z, G2 is just quadratic z to the power of 2 minus an elliptic term. G3 is z to the power of 3 minus a combination of elliptic coefficients and powers of z. So just one power is 1 here, but for higher g's, for higher n, you will get the form, as we said, in the SK. So it's an element in the polynomial ring in the coordinate z with elliptic coefficients. So now important for my talk is the following theorem, which goes back to Zagier in 1991. So for n larger or equal to 0, Gn is an element in V. So let me remind you, V is the set of all special quasi-elliptic functions which have pole order at most 1. And now that the poles have at most order 1, the residues are given by this following formula. It's again, as you see, a polynomial, of course, and it's a specific one. In particular, g to the power of n is regular on the real line for n larger or equal to 2. So I have now two bases. The basis from the integration kernels Gn and my convolutions of z, and the natural question is to compare the two. And here is the result. So firstly, Gn define elements in the space V intersected with the special elliptic special quasi-elliptic functions of degree n plus 1, or if to come back to Atiyah, sections in a vector bundle of rank n plus 1 over x. So when n is larger or equal to 0, then the nth power of z is given by the linear combination of the gk's here, k from 1 to n, and the coefficients are essentially the signed Stirling numbers of the first kind. There's also an addition of a constant, which is known, but I don't want to give it here, it's not particularly nice. However, when you consider the converse transformation and express the gn's in terms of my convolutions, so you get again coefficients which are given by Stirling numbers. This time it's the Stirling number of the second kind, but also the additional constant is rather nice. It's given by Bernoulli numbers. So the proof is, of course, by comparing the residues using the theorem Don Zagier gave us and my own one. And I'd like to mention how to compute the additive constant. What you're using here is that you are integrating over the Gn and the n-fold convolution of z with respect to the real period, and the integrals over the Gn's is given by Bernoulli number over n factorial for n larger or equal to 2. And moreover, the k-fold convolution of z has an integral which is equal to half the full contour integral for k equal to 1, and then you take the power. That's Fubini's theorem. And to be more specific, so this is a small print because it doesn't really matter so much, I give you the first few functions which I obtain using my transformation rule. So G1 is equal to Z, which we mentioned several times already. And then G2 is a mixture of, convolutions of Z and with constant coefficients. And conversely, the convolutions of Z are given by polynomials in the G, and instead of a power, I have the index, which is increasing with increasing convolution. So the GK, the nice thing is that the GK can all be computed from the Konica Eisenstein function. So a few results. Firstly, I'm getting addition theorems for the iterated convolutions of Z using my transformation rule. So the well-known addition theorems for the Zeta Weierstrass Zeta function and the Weierstrass P function yield the following formula for the second order convolution. So Z second order power of convolution power of Z at x plus 1, x1 plus x2 is given by this expression here, where I abbreviated the notation by using this A, which is the sum of the Z at the 2 points x1 and x2 minus 1. And we can easily recursively get higher addition formulas for higher n. I'd like to mention that this result can, for n equal to 2, can also be obtained using so-called phase identity. However, for higher n, the formula don't seem to come out nicely. So I'm getting double formulas, and it's not so directly. It's not very nice. And I would like to come back in particular to my original problem, namely the computation of iterated convolutions of the Weierstrass function P. So that by the fact that the GKs for k larger equal to 2 are known from the Konica Eisenstein function and are regular at x equal to 0, we know what the function z to the power of the convolution power n is, and we can take the derivatives of them. And this way, using this formula here, we can compute the nth-fold convolution of Weierstrass P. So the E2 again is the quasi-modular Eisenstein series. So a nice feature that came up also in my transformation formula is in order to compute the additive constant in my transformation formula. So firstly, the transformation formula was by comparing residues. Of course, this doesn't capture the additive constant. So what I did is to integrate both sides, and then the constant pops out. So the integral over the convolution of Z is just a number, and actually it was a half to the power of k if you consider the kth-fold convolution of Z. So it's a natural question to consider the polynomial, which is defined by this formula, by replacing the specific value of a half here by a variable x. So I will in the following denote my polynomial with Pn of x. And well, my first naive approach was to plot them, and I got, I got nice graphs for small n, but then it became very strange because the higher n, as long as the computer could do it, the more pronounced the shape became a pot form, and I didn't quite understand if this is a trivial thing or if this is something nice and interesting. In particular, I wanted to know if this is if there's an area maximizing or minimizing principle behind. But then a second look at this whole story revealed the following. So I have my last theorem here. So the sequence of polynomials Pn for n larger or equal to 1 is generated by a function I call capital G now to distinguish it from my f I considered before. And it has a quite simple formula given by this expression here. And the polynomials are also have nice properties. So they are, so if the P1 of x is just x, P2 of x is x times 1 minus x. So you have a symmetry around the point a half. So this continues up to a sign. So Pn of 1 minus x is minus 1 to the power of n times Pn of x for n larger or equal to 2. And moreover, something people are generally interested in is the interlacing of zeros. So these polynomials have the nice property that the zeros of Pn and of Pn plus 1 are interlaced. So firstly, Pn of x has n simple poles, n simple zeros, xj, say, of n, so j1 to n, in the interval 0, 1. So x1 for the polynomial n is 0, xn, the last one, is equal to 1. And in between, we have that the j plus first 0 of the n plus first polynomial lies between the jth and the j plus first 0 of the preceding, the nth polynomial for every j. So in this sense, the zeros are interlaced. And really the key observation is a very simple fact, namely the generating function g of xy satisfies a nice PDE, which is given by the partial derivative of g with respect to y, is x times 1 minus x times the partial derivative of g with respect to x. So for n larger or equal to 1, Pn satisfy a nice recursion relation, which is given here. So n times Pn plus 1 of x is x times 1 minus x times the derivative of Pn at x. And another observation is that they are not, these polynomials are not optimal if you compare them with the Legendre polynomials. There is no inner product with respect to which the Pn of x are orthogonal. So to show you a closer look at the polynomials produces the following. So you have the zeros near to 0 and 1, and the computer is getting crazy when you try to plot close to these boundary points. But if you zoom a bit in and consider more the part in the middle, around a half, then you find that the distribution of zeros here, it's a bit, you have a bit like a Gaussian enveloping curve of the graph here. And so they are the scale is also, we didn't see this before, then look at the scale here. We are considering 10 to the minus 50 here. So we have to really to zoom in a lot. So I would like to come to the conclusion and an outlook. So the vector space of quasi-elliptic functions is under complete control. The Gn and the iterated convolutions of Z both yield natural basis for a subspace of the special quasi-elliptic functions with many applications. So I tend to say, you know, the set in some sense are nicer. It's more natural to introduce maybe the set and the piece. Both have only pole order at most 1. But in order to achieve this for the G's, you have subsequently to subtract the poles that are too high, whereas Z never introduces higher poles. It works directly only with first order poles. However, when I actually want to do computations with Z, I have to get back and refer to my functions Gn, which I can compute explicitly from the Konica-Eisenstein function. So each set has its own merits. Moreover, the methods used here should work for arbitrary vector bundles and elliptic curves, and in particular for convolutions of, say, mock Jacobi forms. So I didn't look at this yet. It may yield new insights or new tools. And moreover, the perspective developed here should help with the understanding of higher genus, which is really the focus of my research usually. So I thank you very much for your attention.
Well, thank you very much for a beautiful talk.
I didn't understand you. Excuse me, please. The sound is bad.
He's thanking you for your talk. Thanks, Marianne. That was excellent. I think it's open to questions.
Stanjoy, why don't you moderate the questions?
Happy to do so. I'm happy to do so. Does somebody want to begin with a question? I think you should, people can unmute themselves, can't they, Arthur, and ask a question?
Yes, there's, you can either unmute yourself by clicking the button or by holding the space bar.
Maybe I can just start with just something on your last, one of your last comments, Marianne. You mentioned that there is no inner product with which the PNs are, these polynomials are orthogonal.
This is correct.
In what sense is that true? Is there a Gram-Schmidt orthogonalization that you can do of them, or?
So there's a three-term relation. It's a while ago, I don't quite remember. It's a three-term relation that has to be satisfied and cannot possibly be satisfied in order for the polynomials to be orthogonal.
Okay, so there is no way of turning them into orthogonal.
Yes.
To orthogonal sets. Okay.
So something I tried and I didn't follow up because I thought it's not worth it. When the Legendre polynomials yield a basis, and when I'm expressing my polynomials, it may be that that the formulas between my polynomials and the Legendre polynomials is particularly nice. It seems that the coefficients are predictable, maybe up to the last or so, but I didn't follow this up to high order. So they behave very similarly in the interval between 0 and 1, but the curve, how to say, the pinch is more pronounced in my polynomials in the middle on 0.5. So initially I thought they might be optimal in some L2 sense, and I tried several measures, and it didn't lead to anything.
Okay, thank you.
Marianne, you started out with a discussion of Yang-Baxter. Your number theory, analytic number theory results have some consequences for Yang-Baxter.
I'm not sure I understood you. The sound is quite bad. So the question is the connection between number theory and Yang-Baxter, the implications.
Yes. And the implications of your results.
Oh, with my results. Okay. Well, I actually hoped more would come out. So essentially, when I looked up the explicit calculations, everything reduced just to phase identity, which is of course well known for Kronecker's function. So right now I'm not sure how much I can really contribute to Yang-Baxter equations. So I cannot really comment on this right now. Well, of course, higher genus would be interesting, but I didn't have the time to look into this yet, so.
Just, yeah, I mean, maybe there was one other in your functions Z, which was which wasn't a modular form, but it had it satisfied periodicity with tau goes to tau plus 1, but not with the second relation. But you were differing by 2 pi I, if I remember correctly.
You're talking about my curly Z, right?
Yes, your curly Z.
Yes, yes.
The exponential of it does satisfy periodicity, if I observe correctly. It was a modular form.
Yeah.
It was a modular invariant.
Am
I correct?
I didn't think about e to the power of Z. Okay, that makes sense. Yeah.
I'm just wondering, is there some? It looks like that you're taking the log of some modular form there.
That is true. Yeah, this is true. In fact, so my Z is actually the log of theta. Is how was it? It's excuse me. Usually I know this. It's the derivative, logarithmic derivative. I think it's Excuse me, please. Yeah, it's a derivative.
Okay, that would explain it. Okay.
Yeah.
So, okay. But that's the. Yeah, I will. Is there? If somebody else has a question, please jump in. Val, you usually have a question? No? I don't see any other questions. Arthur, do you have any other question you wanted to ask, or? If not, I think we should.
Well, I think then we should thank Marianne again. And
yes, there's a rich vein of material there, which was difficult to absorb all in one go.
yes.
Okay. Okay. Thanks to Marianne again, and thanks Arthur for hosting this joint seminar.
Well, it was very interesting to have the joint seminar, and I look forward to future seminars possibly joined together. So bye-bye.
Yes. Bye.
Week.
Okay. Okay. Thank you. Thanks again. Bye to all. Bye.
Thank you.